Yes, we are moving on to applications. So the first 12 or first 11 chapters really lay down the foundations of the course, and you learn to deal with specific motions. Now we're sort of transitioning into applications, or what I like to call physics. We finally get to the physics of Physics 1. Not that the other stuff wasn't physics, but you were sort of learning we were sort of learning all the rules, all the big rules that inform physics as we went through. It definitely is physics, but now we sort of, you'll see that the things we're learning in this chapter are very small, like the ideas. There's a lot of ideas. Well, there aren't many ideas, but when it's all stuff you've kind of seen before, but it's applied in a different way to a specific situation. And so we're going to be doing equilibrium and elasticity as one application. We're going to talk about Newton's universal law of gravitation, which is another, which is the first application, if you will. It's one of the cooler ones. And we'll talk a lot about that probably tomorrow or the next day. And then we will try to talk about pendulums and fluids. All right, so we do chapter 15 before chapter 14. We will do some intro to fluids. It will not be on the final, but it is something I like to talk about because my goal with this part of the course is, and we almost never get to thermo. Even though thermodynamics is on the syllabus, almost no one gets to it, but I like to focus on this last part of the course on the things you'll be doing in Physics 2 and in your engineering careers. So you actually won't be doing very little equilibrium and elasticity in your Physics 2 class, but you will have a whole class on this chapter, especially the mechanical and electrical engineers. You'll have to take a statics class. I think the civils have to take it too. I think everyone's got to take statics, usually taught by Dr. West. And you will take his class, and it's basically this whole chapter over one semester. Now, the good news is that if you really get what's going on in this chapter and the last one a little bit, that class will be a lot easier and you'll be able to do it. Engineers like to make it sound harder than it is, but it's pretty simple to just break down things into torques and forces. So without further ado, let's sort of go into, we're not going to do elasticity, but we will do equilibrium. Okay? So let's move on and forth. All right. So in order to talk about equilibrium, we have to sort of define it. So when we look at an object, and we'll look at an object first in equilibrium, it'll make more sense. So this rock is in equilibrium. Okay? And it's in static equilibrium. It looks like it's about to fall, but you'll notice if you were to push on this rock, it wouldn't move all that much, right? So this is the situation we want to describe. Now let's go back up and look at our bullet points here. So when we look at something like that rock, we often want to use forces. We want objects to be stable despite forces acting on them, right? So if we add a force, it won't move. Consider a book resting on a table, or a puck sliding with constant velocity, a rotating ceiling fan, or rolling bicycle wheel with constant velocity. These objects have characteristics. 1, the linear momentum of the center of mass is constant, and the angular momentum about the center of the center of mass at any point is constant. So what we're saying here, I have my number of computer peripherals is growing. I have a game controller on there now. So if we look at each of these, we can say that P, oh, that's the blue is a terrible color. I have to see that. Jeez. I think it's because they're doing yard work down there. So we have P equals constant and L equals constant, right? And so let's take a look at these. Let's pick 2 of these. So I'll pick a puck sliding with constant velocity. All right, let's verify these things. All right, so we want to ask ourselves questions. We have to investigate, right? It's not, I've been saying it all semester, and I'll say it probably my last dying breath will be, it's not about just plugging into an equation. You have to look at a situation and understand what physics you can apply to it. So one way of doing that is looking at a situation, like a puck sliding with constant velocity, and then we know it's sliding. It's not so so you can ask yourself, is it rotating? And I'm asking you, is it rotating? We're just talking about the puck here. No, it's not rotating. Good. So if it's not rotating, that means that omega is equal to 0, which implies that L is equal to 0, right? So we know in this case, for the sliding puck, L is constant. Now, it's sliding with a constant velocity. We know P equals mv. Does mass change? Have we talked about mass changing in problems so far this semester at all? No, not really, right? So we're safe thinking mass will stay constant. Interestingly, mass does change relativistically. So if you find yourself in a modern physics class looking at Einstein's theory of relativity, the mass will actually increase as you get towards the speed of light. So there is a time to consider that, but this is not that time. And then constant velocity by definition means that dv dt equals 0, right? So if dv dt equals 0, that implies that dp dt equals 0 because p is just equal to mv, right? So then, and if dp dt is equal to 0, that also means that p is constant. So we can look at, we want to, when determining if an object is in equilibrium, we can simply look at how it's stated, right? And we can ask ourselves, is the linear momentum constant and is the angular momentum constant? And if we check both these boxes, we can be in what's called equilibrium. All right. Now in engineering and in this chapter, we're going to focus on a particular type of equilibrium called static equilibrium. A puck is like something they use in hockey, Mina. It's a small round disc. Like you can think of this bottle cap as a puck. It would just be sliding along a surface. So it's, oh no, I lost my pen. Hold on. So yeah. Well, I'm still gonna have some fun sliding this anyway. Can you see the if you see the surface here, that the bottle cap sliding would be, oh, you can't see the bottle. The bottle cap would be a puck. Okay. So that was harder to do than I thought it was going to be, orienting that trackpad. That wasn't fun. And the bottle cap was much smaller on camera than I expected it to be. So let's erase. So we can see under, we cannot, it's one thing to state that this stuff is in equilibrium, right? And to look at these statements, but let's look at the argument again, and let's then move on to the rotating ceiling fan. And again, I think I was saying we're gonna focus on a particular type of equilibrium called static equilibrium. That's what you're gonna see in your engineering class, and we're not quite there yet. That's a specific type of equilibrium. We'll talk about that in a minute. So when we look at this, let's look at let's look at the argument again. So we're considering this puck sliding with constant velocity. It's pretty simple. So now we ask ourselves, is the angular momentum constant? Well, the puck is sliding and there's no discernible rotation, right? Any force would act at the center of mass. So therefore, there's no angular velocity, right? So if there's no angular velocity, then there's no angular momentum, and L is constant, right? L equals 0. Then, so we made our check mark here. I'll go to pointing it out. Hold on. All right, now we want to look at P being constant, and we have to ask ourselves this question. So look at what I did here. It says it's sliding with constant velocity, right? Now, if we have constant velocity, we know that our linear momentum is equal to mv. We established that m does not change in classical physics. And we know that at constant velocity, dv dt equals 0 is true. So if this is true, when you integrate up, dp, or you don't even have to integrate up, if dv dt is equal to 0, that implies that the momentum change with time is equal to 0. And if you integrate this up, you get that p is a constant. So this is in equilibrium. So this would be what we call dynamic equilibrium. All right. Now let's look at another one, because you know this is right, like a rolling bicycle with constant velocity, but a rotating ceiling fan, they really should have said a rotating ceiling fan with constant angular velocity to be right here. And we're gonna make that assumption, but let's look at the next one. All right. So now we're gonna concentrate on this rotating ceiling fan, but we're going to add the caveat here that it has constant omega, where omega here is angular speed. Okay, so all right, I'm just making sure my timing for my meetings is working out. I don't know why. Okay, so if we do that, all right, let's ask ourselves the same questions. First, let's look at linear momentum. What's the velocity of a ceiling fan? Its translational velocity. Look up at a light. Is your light moving? Imagine your light has a fan. Maybe it does, maybe it doesn't. But is that fan ever translating, or does the light fixture stay in the same spot? I'll give you a hint. I gave it away with the term fixture. Right, it stays in the same spot. V equals 0. Okay, so V equals 0, that implies that P equals mv equals 0, right? And we have P is constant. So this one checks out. We're in angular momentum, or where our linear momentum is constant. So now let's go to angular momentum. So we have L equals I omega, right? That's one way of looking at it. But another way to look at it too is that if L is I omega, we know that dl dt equals torque, right? So if the angular momentum is constant, there should be the torque here should be 0, right? And when we look at it, if we take the derivative, I is constant and omega is constant, right? So we know that if we take the derivative, we get 0. So dl dt is equal to 0, which means that these are constant, and the torque is equal to 0. So we can see that for angular momentum to be constant, the torque actually has to itself also, well, I think the torque's got to be 0, right? If the angular momentum is constant, just like the forces have to end up being 0. So when we get there, in equilibrium, these just have to be constants. They don't have to be 0. In the rotating fan case, we happen to have 0 here. No, we have in the rotating fan. I'm sorry, that's wrong. That's really wrong. In the rotating fan case, we have a constant value here for the angular momentum, and we had 0 And for the sliding puck, we had a constant value here and a 0 value here. But in this chapter, when we look at objects in static equilibrium occurs when P equals L equals 0. So not just constant angular and linear momentum, but 0 linear and angular momentum. And this will set up our rules for static equilibrium. Now, this is going to seem easy from an equation standpoint, and in some ways it is, but I remember, just personally, this chapter being the most challenging chapter of Physics 1. And again, the equations are easy once you set them up, right? The math is not hard, but identifying what direction forces go in complex situations is difficult. And particularly if you're like me and your brain mixes up right and left. This chapter can get out of hand it got out of hand pretty quickly. So I want to encourage you guys when you're working on problems here to sort of slow down and just be very careful and don't rush. And again, I've noticed a lot of people. It still happens. I mean, it's funny. I'm not even kidding here. If all you get from this class is that you slow down and read problems carefully, I'd say you've gotten a tremendous amount no matter what your grade is. If that's all you get from the class, is that when you see a problem, you don't just assume you know what the answer is going through, but you look at it, you think about it, and you frame it, I would say you've gotten a tremendous amount. And I still had people yesterday in the Physics 2 exam, so they're like a semester ahead of you going, oh, I didn't read the problem carefully. And about 80% of the time when I help you guys with homework in the office, back when people would come in the office, it almost always comes back to not reading the problem carefully. So in that sense, the equations are easy, but setting up the problem and being very careful about it is not trivial at all. Okay? So, only one of the previous examples from the previous page is static equilibrium. Oh man, it gave it away. I was going to say, we'll go back and look. But the book resting on the table, right, fulfills these conditions. And again, when we're looking at static equilibrium, I think it might be obvious. You can see here, if P and L have to equal 0, we can look at not just point-like objects in static equilibrium, but full rigid bodies as well, which is what we're going to be concentrating on. So let's move forward, and this brings us to our rock, right? Our rock that we first started picturing. So we discussed stable versus unstable equilibriums in Chapter 8, and I want to draw the energy diagram for you again because you just sort of saw that. So if we have an E versus X diagram, right, and it looks something like this, just something weird. You'll notice that a point like, I'll change colors here. I'll use blue because I can't hear. You'll notice that points like this, you can balance on them, but any small movement, right, you will leave that position and you won't return to it. But here, at a point down here at a bottom or at a valley, here the object, if you move it a little bit, tends to settle back at the same spot. So this is what's called a stable equilibrium, and this is an unstable. So I'm just going to write them with U and a S. Stable, unstable. So if you look at the rock here, looks can be deceiving, right? It looks like it's about to fall over, but you'd need a lot of force to move this rock, right? You could probably take a funny picture in the crevice here and make it look like you're holding the whole rock up by yourself. That might be scary, though. I mean, it's not going to fall, but I don't know that I'd do it. But despite its appearance, it's very much in a stable equilibrium, right? If it were an unstable equilibrium, even the smallest breeze would topple it over, okay? And we're going to find that whether we determine something like this rock to be in equilibrium, we're going to have to introduce a new concept that's going to sound like it's similar, and in this class, similar to an old concept, and in this class it will be, but it isn't, you know, in all cases, and that's the center of gravity. All right, so we'll get to the center of gravity, not yet, but we're going to get there soon. But the center of mass and the center of gravity, when they're the same, static equilibrium problems will be solvable, and that's the case we'll look at here. But let's take a look at a simpler object that we could all put on our desks. So if you have a book, I'd suggest you grab it and just play with it, right? Let's see if we can find it. All right, so I've got a book here. This is called Modern Classical Physics, if you can see it. So this is basically a book of it looks at the physics we've learned, and it looks at it geometrically instead of dynamically. So it's how Einstein pictures the universe. It's pretty interesting. So I'm gonna feature the book for a minute. Can you all see the book standing there? Any other crap in my office? All right. So if we look here, part A of the figure, it says we have an unstable equilibrium. All right. So let's see if we can. Let's see if we can get this in an unstable equilibrium, balanced on its edge. Well, I want you to notice something, because I won't be able to actually balance it on its edge. But you'll notice if I let it go here, it falls back. If I let it go here, it falls down. Now that's a big, heavy book. I don't know that I want to break my desk, but it's my desk moved while doing that. But that means physically, right, that there must be some point at which, instead of falling one way or the other, it will try and guess which is which. Now, because of all the small imperfections, there will always be something pushing on the book, or like in this case, like I've got a cord pushing on it. It's resting on a cord. So that'll affect the equilibrium. But it should be possible with enough fidgeting, right, to get it to just rest. And I can almost do it, right? You can almost see it happen. It's good to have big physics books. I don't usually bring them to class. So in the supporting edge, that would be an unstable equilibrium. Right, like the rock balancing in the sculpture. Well, no, the rock balancing in the sculpture is stable, right? In C, this is actually more like the rock balancing, because you'll notice I can push on it and it stays up. All right, Einstein would have more interesting descriptions of why it stays up, but you know, that's a little beyond what we're doing. So we can see that a bigger object like a block, or if you look at the universal power supply there, if you that's a special plug I have because my power doesn't work in this place very much. That is going to be more stable than the book, right? I don't want to push it too hard because I don't want my computer to fall off. But you get the idea. You could look at, or maybe something better to look at would be my server back here, right? That's in stable equilibrium, even though it's hanging off the wall there. All right, so that's enough exploration of Dr. Tolan's office, I think, for one day. But do you understand the difference between that stable and unstable equilibrium? I'm going to put my book back. Oh no, I dropped many other books. Oh no, I believe I've made too big of a mess here. You think I would have used some of this Corona time to do the explorations in space-time I wanted to do, but it's actually been pretty busy. So let me get the webcam back up to my face here. There we go. That's a really good question. I would say that it is a platform object interaction, right? So if you shave away that platform, the smaller you make the contact point, the more likely you are to be in an unstable equilibrium. And you'll notice that we sort of make that point here looking at block D, right? They're saying the block is even more stable, and that's because it's not necessarily more massive, but it contacts more of the surface. So, and you'll notice for our unstable surface, right, our unstable equilibrium, there's only one contact point, right? The point or a line of contact in the case of the book. Here you're resting on a surface. You have an area of contact. So I would say the larger your area of contact, sure, the more stable your equilibrium. Right. Yes. Yeah, Nicholas, that's correct. Now you can always add a big enough force to destroy the equilibrium. It's like think of it this way, right? My house or anyone's house is in stable equilibrium right now. Yeah. In an unstable equilibrium, even the smallest force will throw it off the equilibrium. But what I mean by I was previously saying, if you apply enough force, you'll break through a wall, right? You can get a wrecking ball and knock my apartment building down pretty easily, probably. But if I punch the wall, it's not going to make the building crumble, right? So you can always exceed the equilibrium of an object. But when we talk about static equilibrium, we'll talk about the conditions to achieve static equilibrium, like where is it that past this point we're static, and maybe past this point we're not, things like that. Yeah, so that's the kind of stuff we'll look at. Oh, you're talking about the Millennium Tower in San Francisco, which is doing just that. Probably not. It's in stable equilibrium to the effect that it's not imminently collapsing, like a small breeze won't push it over. But again, over the long term, it's not. I would call it an unstable static equilibrium, right? Because it's slowly crunching. Well, there's stuff that's designed to sway with the wind, so that would be different. And again, the structure's uprightness would be in static equilibrium, but the structure itself would move, and that's where elasticity comes in after in the second part of this chapter. But again, I just don't cover it. But yeah, you can deform. Looking at the deformation of rigid objects is itself another layer on top of this. Yeah, but we won't really cover that. But there are foundational problems in some buildings where the building itself is actually, if it goes past a certain point, it will tip. So it's in static. I guess the right way to answer your question, Daniel, is to say that it's in static equilibrium until it's not, and we're going to solve problems like that, right? Like imagine again the pad. You can't see the pad. I keep thinking you guys can see the pad. So imagine this. You have this pad in my hand. If I walk along here, I'm in static equilibrium, right? Nothing's really changing the force. It's there. It's stable. Nothing's really happening. But if I walk past a certain point, this starts to tip. So it's in static equilibrium. So part of what we'll do is we'll figure out when something can and can't be in static equilibrium. And when you look at those buildings, if they reach, when they're designed, if they reach a certain tipping point, or you reach a distribution of forces, if the center of mass goes beyond a certain point in the system, right, the building will collapse and won't be in static equilibrium. So you can go from static equilibrium to non-static equilibrium, definitely. Okay? Well, life is terrifying. The world's a terrifying place. So, all right, good. Okay. All right. So, this irritates me. There was an error in transcription. Let me go and see. Make sure that that's not super important. Okay. All right, so the requirements for equilibrium given by Newton's second law in linear and rotational form is this, right? So recall that, let's look at this from our last, oh, blue. Let's look at this from our previous slide, right? So for static equilibrium, L has to be constant and P has to be constant. This implies that dLd equals 0. And remember, that's also equal to the torque. And this implies here that dp dt equals 0 equals F. So we can see where these equations come from. Balancing the torques and the forces, but this doesn't put us into static equilibrium. If we want to be in static equilibrium, we have to have the additional requirements. Hold on, no, we're not there. I looked at the wrong thing. Darn it. That's the problem of going from one to the other. So we're still in equilibrium. So here, the vector sum of all external forces that act on the body must be 0. The vector sum of all the torques that act on the body measured about any possible point must be 0. So this is important to get back to. And what's important here to understand and to realize is that you can have forces and torques acting on these bodies in equilibrium. All right? It's not that there is no torque or force acting on these objects. It's that they all add up to 0, right? So if you think of, you can think of someone that when we look at our book or our block resting on the surface, that's easy, right? But now imagine you have two people pulling on a block, right? With T1 and T2 that are equal. All right. Now imagine that people are applying torques in opposite directions. Torque 1, torque 2. Right? A lot of stuff could be going on in this problem, but the net result is the block stays in the same spot. So that's the one thing to keep in mind. All right? It's not that there are no forces, it's that they all add up to 0. It's not that there are no torques, it's that they all add up to 0. And remember that force and torque are both vectors. So you have to be very careful when you add them. And as always, if you're struggling with vectors, I encourage you to go do more of your vector extra credit marathon assignment. Now for static equilibrium, all right, we often will have two additional criteria, which is that the linear momentum and the angular momentum themselves must be 0. But when we look here, we can look at, since we're looking at vectors, and we usually use a right-handed coordinate system, we usually break things up into these directions, right? The force will have x and y components and be in the xy plane, and the torque will be in the z direction, okay? So we generally pick an origin so that the forces lie in the xy plane, if possible. We won't always, but for the most part, that's how it'll go. All right. So we've already defined this. This sort of summarizes it and gets us ready to solve problems. So I want to go through, I think we have a checkpoint next. I hope we do. Yes, good. So I want us to start thinking about this, all right? And I want you to take some time. I want you to take 2 or 3 minutes and see if we can answer this checkpoint, all right? So the figure gives 6 overhead views of a uniform rod on which 2 or more forces act perpendicularly to the rod. If the magnitudes of the forces are adjusted properly, but kept non-zero, in which situations can the rods be in static equilibrium? So what I want to do is, I want to go over what you can and can't do. So these forces always have to be acting, but they can be made as big or as little as you want. But you can't turn it off. You can't set it equal to 0. It's always got to be a little bit there. So what I want you to do is I want you to take 3 minutes or so, 3 or 4 minutes, and I want you to evaluate each situation and see if you can guess which ones it is. Now, if you have a question, feel free to ask, but if you're struggling and you don't want to ask a question, that's okay too, because what I do want to do is you can feel free to put the answers, but I just want you to know we are going to go over each one and ask, but I want you to work on it first. Again, it's just a lot more useful if you work on it and figure out what you're not getting, and then when I go over it, you can say, oh, that's what I didn't get, instead of going, oh yeah, that makes sense. So that's a more useful way to do it. And either way is fine, but we will go over each one. So play with it for a little bit and see if you can, what you come up with. All right, which one of these can be kept in static equilibrium and which ones cannot? Yeah, Mina.
My question is, like, can the road turn around? Like, can it revolve? Like,
Yes.
it can revolve. Like, we
Yes.
can imagine it as actually we're watching it on top on the
Yeah.
surface. Okay, that's what. Well, okay, that's what I want to clarify. Thank you.
Yeah. No problem. They can have different values, Nicholas. Different values. You get to turn a knob. You just can't turn the forces off, because if you set them all equal to 0, then the problem's trivial. So yeah. Okay, we've got one answer coming in. So let's take a look. All right, let's take a look at all of these. Now, with forces, it's a little trivial. And what I mean by that is you can always add these forces, and when you look at them, getting the forces to equal should be trivial. So you can always cancel out forces. So far, everyone's in good shape, right? So that means P will equal 0. Ah, we have some disagreement. That's always good. Now let's look here. Let's look at the torques. This force, right, will tend to cause a clockwise rotation. So this force here, so ask yourself if you see that. And just, if you see it, look here. If I push up on the pen, or if I push up here, that will cause a clockwise rotation, right? Now, the same thing if I'm on the other side and I push down, here, this too causes a clockwise rotation. Right, both of them cause a clockwise rotation, so if they're non-zero, this will always have an external torque, right? So in that case, L will not be equal to 0, and we can't be in static equilibrium. So A is out, right? Now, if we look at B, B is a similar situation, but now it's counterclockwise, right? We're looking at them each one at a time. So here, when we look here, each force will be complementary. They'll both lead to clockwise rotation. Okay? So when we look at that, L can't equal 0 because they can't cancel out, right? Even if, no matter how small you make them, you'll always be adding 3 positive small numbers together. So this one can't be true. Now, if we look here, you'll notice we have clockwise, or counterclockwise rather, and we have, again, it almost looks like we're in the same situation because we have counterclockwise, but this one causes a clockwise motion. So because we have plus and negative, and we can switch, if we make this one, we can make this one substantially bigger to cancel out the effects of these two forces. So it is possible, or these two torques rather, I'm sorry. So it is possible for this one, for L to equal 0. You can create a scenario where L equals 0. And since P equals 0 for all of them, C can be made to be in static equilibrium. All right? So I think you can kind of see going forward here, with D, you have one direction. This will cause it to go counter. I'm having a hard time visualizing it right now. It's stupid. Counterclockwise. This, if you pull it, you might want to argue clockwise, but then this one will go counter and counterclockwise. So I don't think it's. I think with this one, what you'd argue is that this one is going to pull because there's no fixed pivot point. That this one will pull without something in the opposite direction over here. That won't actually make it go counterclockwise. That you'd still be pulling with the same idea that's going here. So in this case, you can't add them up. L doesn't equal 0. Because no matter how you do it, you're always going to be rotating. Yeah, Amina.
So on D, if we were extending the arrow looking downwards on the right side, like it could, no?
No, I think if you extend it down, you're talking about this one, right?
Yeah.
So we extend that arrow down. Let's see. Say that that one's big. All right. So how are we going to counteract it? It's important to. Part of me wants to say it's on the opposite end here of this pivot, but then I'm just trying to imagine. Yeah, I guess if we pulled down here, so we'd have these two. So you have this one going down. That's going negative. I think the argument here, because these two would be going clockwise, right? Or pulling it counterclockwise. That one is also making it go counterclockwise. So you're saying if this one was 3 times bigger than those, that they'd have each other out. But we don't have a fixed.
Possibly, yes, because the way I see it, the A and B, they were all making the road move towards the same direction. However, from C to F, there is resistance. There is applicable resistance to the movements
Right.
at some point, some sort. If you make adjustments, if you don't make adjustments, it's a different story. But the question says, if the rubric says, if the magnitudes of the force are adjusted properly.
Right. And my issue here is if you look at C, E, and D, E and F, we'll come back to D. If you look at E and F, you sort of have the not only the forces opposing each other, but you have them opposing each other in such a way that you have one. You'll notice here you have this one. The opposing one is in between these two, right? And you'll notice that that's the case here. You have a force here, and this is in between, so it can really balance it out, and the same thing here. So we're going to find that in the same way we can check these off. Now, even though it seems with E, my problem with C is that, or with D, is it seems that you don't have that. So you have one effect. To me, what it looks like is you have these downward ones and these upward ones causing the same motion, because and mostly because there's no fixed pivot point. And what I mean by that is, in order for there to be the resistance, I would think that you'd have to put this force in between here, right? And you'll notice they do that. If you put this force just on the other side, it can resist it. But on here, it seems like everything is like the two forces will do the same thing. You know, these will both lead to this counterclockwise, and these two will both lead to a counterclockwise motion. If you have a fixed pivot point, right? If you can only pivot about this point, you might have a point there.
Okay, got it.
But yeah, but based on how we're looking at this block just sitting there, that's how I see it. At least when I look at it initially, I can see what you're saying though, and like it you know, I think this one is definitely the hard one. It's definitely confusing, but I think because the forces don't act relative to each other in the middle, you know, in between other forces, like you have here and here and
Yeah,
here,
I guess the
you
distance from the
won't get
center.
that resistance.
Yeah, the
What?
center of gravity is it plays a role.
Yeah.
Okay.
Okay.
All right, thank
So,
you, Professor. I said
So,
thank you, Professor.
oh, you're welcome. I couldn't hear. My volume's down. I was listening to music. I'm sorry, I mean, I didn't hear you. But
No
I heard you.
worries. No worries.
Yeah. All right. So, as we can see, C, E, and F are our correct ones. And again, they have that feature of the opposition force acting between the other two, right? And you'll notice that each of these, in order to cancel out, you need at least 3 torques, and one of them has to act between two of the opposing forces. So let me show you in blue what I'm talking about here. You have this setup here, this setup here, and the whole thing here. All right. Okay. So what I want to do is, we are going to be ending a little early today, and that's okay. Probably 10 minutes, 10 to 5 minutes or so. But actually, no, wait a minute. No, we're going to be any more early than that. So I want to take a short 5-minute break, not like a 10 or 15, because I need to sign off by about 2:55, okay, which is 20 minutes early. So it's not ideal, but it's what I have to, but it's what I got to do today. So let's take just a short 5-minute break, get some water, don't go too far away, and basically at like 2:02, I will be back on the horn, and we will continue with our equilibrium discussion. Okay? All right. I'm going to go get some water. Okie dokie. I am back and water equipped. All right. So, I don't have my... Actually, I will be back. I want to get my phone to take attendance eventually. Then I'll need it. All right. I'm back. Okay. I'm back for real this time. Even though my camera's doing that split thing it does, that's all right. It'll work itself out. Okay. So moving forward, so now we get to what I told you about, the center of gravity. So now it's interesting to think of gravity this way, right? Because basically, if we look at a rigid object, well, when we look at an object, we're used to looking at a car, an airplane, or anything as a point and saying all of the mass is at this point, and we use that approximation. And even though the variances are small, if you remember, I actually had you look in your one of your earlier lab reports. I had you look for how fine with what precision you could measure changes in the gravitational force. And you will note that there are resolvable differences between f of g on your feet and f of g on your head. We can call that fg1 and fg2. Now, for most purposes, fg and 1 and g2 only vary by somewhere in like the 8th or 9th decimal place. But they do vary, and it is measurable. So when we look at the center of, when we look at something here at a object, we look at the gravity acting on each point of the object, and we can simplify this by looking not at the center of mass necessarily, but the center of gravity, right? So if everything works here, if the gravitational force acts on each little point along the body, we can say that the gravitational force on a body effectively acts at a single point called the center of gravity. If the force of gravity is the same on all points of the object, then the center of gravity is the center of mass. However, in something like U, they'd be almost the same. They'd be indistinguishable at our scale. But if you zoom in far enough that you can tell the differences, you would be able to resolve them as different locations. Again, because gravity is slightly different on your head than and your feet. When you look at an object like the Earth, right, where gravity and mass are not evenly distributed the same way, the force of gravity is not the same everywhere on the Earth. The center of gravity of the Earth and the center of mass of the Earth are two distinct locations. All right? Now, we've assumed that they're the same up to this point, and we will notice that they are different, but they will still continue to be roughly the same. We'll just recognize cases where it's not exactly true. Okay? And you'll notice they define it. X center of gravity is actually defined in a sense very similar to the center of mass. But again, this is the case, right, when the force of gravity acts uniformly across the whole object. All right? So there, I believe what they're trying to show is that the center of gravity is the center of mass. But again, we want, that's now something to think about, right? Can we use that approximation? So now we want to shift to some examples of static equilibrium, and examples of static equilibrium are mostly effective in drawing the forces. Once you draw the forces, because you have that experience, if you have the correct diagram, the problem is about 80% done. Once you've written the equations down correctly from your correct diagram, you're about 95% done. After that, you're algebra. It's all algebra. Now, that being said, with some of these problems, ironically, setting up the forces and setting up the equations can be very simple, can be very short, right? It can be 2 or 3 lines of math, whereas the algebra might take a page or two. So sometimes you have to remember that we now have, in addition to F, Y, to F in the X direction, F in the Y direction, we now have torque in the Z directions, effectively allowing us to solve for up to 3 variables. All right? So let's take a look. Oh no, wrong key. All right, so this gives us a good checkpoint 2, and this is what problems will start to look like. I have a few of these examples for us to go through. We only have the 1 checkpoint, but we'll have a few more examples. So let's take a look and see what it has to say. Now, the figure gives an overhead view of a uniform rod in static equilibrium. So let's take a look at what we have here. We have forces acting on the rod, right? And we have the distances, it has this length L, and we know that these distances between forces are given here. So this is the given information, right? So the first question is, can you find the magnitudes of the unknown forces F1 and F2 by balancing forces? So think about that for a minute or two, and all will be revealed. All right, well, the easiest way to do it is to harken back to chapter 5, just sum the forces in the y direction. And for a rigid body, we just go on and count them. All right, so we got 20 going up, minus 10, minus F1, minus 30, plus F2. That's got to all equal 0. How many equations do we, so we don't have a torque equation yet, and we're just adding, it says just by adding forces. Yeah, Mina.
Professor, the 10 Newton force, will it effectively do something because it's at the center of mass, no?
Well, you got to look at it this way. Right now, we're just adding forces, and we can't assume there's no non-translational moment, or no, we can't eliminate linear momentum. So right now we're just looking at whether, do you see the pen? We're looking at whether the bar goes up and down.
Okay. All right.
So we're not looking at rotation yet. We don't have a
Okay.
torque equation yet. That's what I meant by we don't have it. So the 10 Newton force will move the bar down by itself, right? If that were the only force acting on it. So, but in order to be in equilibrium, both the sum of the forces and the torques have to be 0, but we're not at torque yet. We're just balancing forces. We only have one direction here. So we effectively have one equation and two unknowns. So can we solve this? Can we solve for both F1 and F2 here? No, we don't have enough equations, right? So we can simplify this for sanity's sake to to 20 minus 20 minus F1 plus F2. That's going to equal 0, right? So now it says if you wish to find the magnitude of F2, so we want to find F2, right? Where would you put your pivot point? So it's up to you where to put the pivot point. If you put it here, and this to get to Mina's question, if you put it here versus here, that could mean different effects for all these forces. So it's up to you to put the pivot point at a place to sort of look at where you can solve for these things. So now you want to be strategic about your pivot point. And yes, you only solve for the system at where you put the pivot point completely, but the pivot point can tell you, if you put it in a certain place, you can resolve F2. So you'll notice the one thing I would remind you of when thinking of where to put the pivot point is you know you're going to want to sum torques, and torque is equal to R cross F. All right? So if you put the pivot point right here at F1, you'll see something interesting happens, right? When we sum the torques, we're going to have, around this pivot point, we'll go one at a time. So we have the 20, this is going to equal 460, this is going to equal 20 times 6d, right? And is that going to be positive or negative? That's going to lead to a clockwise rotation, it looks like, about this pivot point. So I'm going to call that negative. All right. And then let's go to the next torque. You just do them one at a time. This one will cause a counterclockwise rotation, right? If you're having trouble seeing it, just use your right hand rule. That'll help. So you have R cross F. You stick your thumb out. This one will go towards you. The other one will be minus. You can also use your right hand rule. It's harder to do via this camera business. So this one will be plus 10 times 2d. Or no, yeah, 2d. And then notice here when we get to F1, I shouldn't have put that equal sign there. That's premature. Notice when we get to F1, it's going to be plus F1 times 0, because the distance from the pivot point to F1 is 0. So that effectively eliminates F1 from our equation, right? And then we can look here. F3 is going to lead to a counterclockwise or a clockwise rotation. And so that's because, remember, we've crossed to the other side of the pivot point. And when we look at that, we can write that as minus 30 times d. And then we can write plus F2 times 2d. And that all has to equal 0. Now, one thing you should notice is that you can factor out the d's out, and you can reduce the equation. I'm going to write it up here. 20 times 6, this will be minus 120 plus 20 minus 30 plus F2 times 2, right? And that's all going to be multiplied by D, and that equals 0. So you can just divide by D and get rid of the D right away, or divide by D and cross it out. It doesn't go to 0. It's just there without losing generality, and you can solve for everything in here. And now you can solve for F2. There's just one variable and one equation. So you don't even need to know what D is to solve for F2. All right? So if you do this, you'll find that F2 actually turns out to be 65 newtons. And so now it's asking you what's the magnitude of F1. Well, it's pretty simple. This would be 20. You just plug F2 in here, and now you can solve for F1. All right? And you should get 45. Yeah, you do. Any questions on that checkpoint? Okay. Important, I want to go over some key ideas first, just to sort of summarize in case you see it again. So that hopefully it'll all, even if you're, I'm glad it makes sense to some of you. But keep in mind some things. First, when you sum the forces, that's translational. Don't worry about it rotating. You just add them all up, like we did here. You'll notice they're all in the y direction here. This won't always be that easy. We're going to see, not in the next example, but in our final example where this gets a little more complicated. But when you're looking at torque, you have to keep in mind, just do them one at a time. All right, you want to pick a pivot point to eliminate one of your unknowns. It's a crafty way of eliminating an unknown. And then you want to go through each torque and set up your equation, and then see that everything falls out or doesn't fall out, right? You'll need to make that distinction. And then you can add them up. It's just algebra. But I want you to see that this small example could potentially have quite a bit of algebra. I mean, I skipped a few steps because, I'm taking a chance here. But that, whenever you skip steps, you have a real possibility of messing up. But we've got only like 4 lines of algebra here, but this is also the simplest problem I could probably think of. Okay? Even though it's a checkpoint, I didn't think of it. It's one of the simpler ones we can do. Okay. So, again, when you have your torques, you just want to do them one at a time and not go crazy with it. Now, I like this example, this next example, because it's a little weird, right? There's 2 scales going, there's 2 blocks. It's a little more complicated. All right, so what I want you to do on your own is I want you to make a simplified picture with all the forces on this block. And what you're going to have to do, and I want you to sort of create your own equations without worrying about what the numbers are, and that'll be our first step. Okay. Identify all the scales. You can call this this will be the scale 1. We could call this the left. That didn't work out right. Call this left. And we can call this right. I'm going to give you about 5 minutes to try and set this one up. Hopefully it doesn't take you that long, but I want you to. Maybe 5 minutes is too long to give you to do this. I'll give you another minute or two. 2:28. I'll jump in here. So if you're struggling, I'd say keep it simple. Well, I'm not there yet, Daniel. So I don't know. It depends what I ask. But I have a feeling, yeah, you're probably right. All right. So let's draw these. So the easy ones are we have two forces that go down, right? Hold on, let me. Well, we'll see in a minute. Let's see what the I haven't asked a question yet, so we'll get there when we get there, and then we'll see if it depends. I think Daniel has anticipated my question. It says he anticipated it correctly. So we have two We have two forces going down, and we have two forces from the scales going up. Oh. All right, so we can call this F left and F right. And we can call this one big mg, and we can call this little mg. Now the question is, given big mg, or sorry, we know g, right? Given big M and little m, all right, find FR and FL. And to answer Mina's question, your pivot point might depend on your torque equations. The way they look might depend on your pivot point, but your scale readings for FL and FR, if you think about it, just think about it physically, should not change regardless of where you're rotating, right? It doesn't matter where you're rotating about. These should have the same reading. Yeah, Mina.
I'm a bit confused. Are there
Good.
actual readings on the scales? Like there are numbers there? I don't
Yes.
see them.
Oh, well, you're not going to see you could just, can you see, you're not supposed to see the numbers.
Oh,
but
okay. Because the
yeah,
way you
there's
said, I thought it was like I was like, okay, there are numbers there and I don't see it. Now I get what you're saying. Okay.
Yeah. No, there's readouts in the scale, and those readouts will be the same, irregardless of where the pivot point is.
All right, got it. Thank you, Professor.
Okay. So now the question is, can you solve for F of L, F of R, M, and M, for F of L and F of R? So this is actually the same as the last example we did in a lot of ways. The first thing we want to do is start off with summing the forces. Switch to red here. So you'll notice we only have forces in the y direction, so that's convenient. And that will be equal to FL minus big mg minus little mg plus FR, and that's going to equal 0. And we're in the same situation we're in the same situation that we were in last time, right? So what we want to do is we just have to pick one, right? We can pick either the left or the right. If we pick the left for a pivot point, we can sum the torques about, we'll call this point O, and that's going to equal our first contribution. FL gets eliminated, right? It's 0. And then we have, if we're choosing this point, this will be this will cause it to move clockwise. Wait a minute. That's counter, right? That's clock, so that'll be minus mg, because that's the force. I'm writing these g's in an inconvenient way. I'm going to change that. I'm going to move it up. And that will be times r, we can't forget that part, times L over 4. All right, and then we have plus mg or let's see, we're at the pivot point here, so this will, downward forces will always, downward forces will always tend to go clockwise, so that'll be minus little m. That's going to be L over 2. And then we're going to have plus FR times L. And then, of course, it all equals 0 because we're in static equilibrium. So now, using the torques, we are able to eliminate one of our unknowns with our choice of pivot and sum the torques about that pivot. Now, if you pick another pivot point, you can create 2 equations and 2 unknowns, and you're creating a lot of work for yourself. We're picking a pivot point to make our lives easier. And that will often be the most challenging part of problems in this chapter, is picking pivot points to make your life easier. But that being said, you can certainly pick any pivot point you want, and as long as you're consistent, everything should come out fine. So when we look here, we can see that right away there's an L in every term, so the L's we can get rid of, right? And we can write that FR equals big M over 4 times G plus little m over 2 times G. And that's it. I think that is that what you got for the right? Yeah. Okay, 1/4 m plus 1/2 2. Okay, yeah. So now you could sum the torques again and put another pivot point if you'd like, but once you have this equation and you know everything, and you have say you just had a number, you could just plug FR back into the original equation here, and you'll get, you could solve for FL. So if you do that, you get I'm just doing the algebra in my head, which means I'm very likely to get it wrong. But you have 1 minus 1/4, which is 3/4 big mg, and you have 1 minus 1/2, which is plus 1/2 little mg. That should be FL. All right? So yes, so Daniel, you anticipated the question correctly and were correct. So everyone, take a minute to look at that and see if you have any questions. Again, I find this to be difficult. What I'd like to do to start tomorrow is, because I don't want to, I'd like to spend 20 more minutes. We have another example. I'm not running out on you yet, but I'd like you to take a look at the homework tonight and try working on it yourself, and come back and we'll try and answer some of the questions. We'll answer a homework question. All right, that's what how I want to start off tomorrow, so that we can actually see a more complex torque question. Okay? So that's your assignment. We're not done yet. Don't go anywhere. But because we have another example, I want to show you a 2D example, how to set up a 2D one. First, but I worry very much in this chapter, because I remember being a student watching Dr. Thompson, my professor, my physics 1 professor, do this, and when he did it in class, it's like, oh yeah, it's so easy, it makes so much sense, and every time I'd go home, I'd go, wait a minute, what? And I got it. I eventually got it. I mean, I'm here teaching you guys, but it's don't take it too lightly. That's all I'm saying. Think about it and really dissect it. Okay, so ready for a harder one? Well, we'll see if you put some numbers in it. we can see everything written nicely. So I'll give these slides some time to be paused on too if you want to go over it on your own. You can see here that you have a much nicer written diagram than I have, but it's the same thing, right? And we saw again, as we did last time, that the vertical forces were not enough. We had to balance the torques. If we picked our pivot point on either side, we could eliminate that force and solve for the other. And you'll notice they just do some math and they figure it out, right? And we did a little bit of a better job, but we got this term here that's the same. You'll notice you can see here that the L's will naturally cancel out. And they just gave you some numbers so you can plug those in. If you want to see it with numbers, you can try going through and plugging those in and seeing if you get 15 newtons on the right side and 29 newtons on the other. All right. So hopefully that makes some sense. And if you wanted to see it with numbers, this should give you everything you need to do it and check to see that it makes sense yourself. Okay? All right. So our last example of the day is going to be this wondrous example. Not so easy now, huh? So I want you to struggle with it for about 3 to 4 minutes. So around 2:43, I'll chime in and we'll draw the force diagram, the force and torque, the force diagram, and then we'll decide where to put our pivots. Okay. So one thing to keep in mind is that the object of interest is the beam. So that's what you want. You want to draw your forces on the beam. Fun times, right? But this is what you will typically see. Yep, Mina?
So in this more realistic scenario, it shows we will have three equations, right? One for the
Right.
SF on X, then
You'll have X
SF Y,
equations.
and then the torque.
Right. You'll have an X equation, Y equation, and the torque equation, or the Z equation.
I just want to confirm. Thank you.
You're welcome. Yep, Mina?
All right. So in my viewpoint, right, I tend to break down when I have something complex. So the way I see it, I have two systems. I have
Sure.
I have the weight and the tension on the rope from one aspect, and then I'm looking at the beam
Right.
itself, right?
Yeah.
Where I get confused is how do I depict the force on the hinge. Like,
That's the hard part. That's the part I expected you guys to have trouble with, and that's the new part. So the hinge you can think of as a force.
because I remember when we have a system with a rope with tension here, tension there, it's the same thing. So you can, so this
Right.
is your connecting points. But
You
I'm not very sure here how
you
they're
can
connected.
you can think of the hinge as pushing as sort of this normal force pushing along the beam from the wall. It's not normal to the wall though. But it's this force push of the wall pushing of the hinge pushing straight along the beam. And that's force hinge.
I see. And when we're breaking it down into X and Y, that's when they're gonna.
Okay, you got it.
Okay,
Yep.
got it. Thank you, Professor.
You're welcome. So right, so up 244. So that's the hard part, is this force of the hinge. Now, let me ask you something. The force of the hinge can be complicated to really express accurately. So let me ask you, where do you think you're going to put your pivot point? Yeah, Mina.
I mean, I would have to find a place that go my life easier for sure.
Right.
So
And if the hinge is and you've already identified the hinge as the weirdest force, right?
that is correct. So I would go to probably there to put my pivot, so I can eliminate the.
That would be a very smart idea. So the pivot point you want to pick is the hinge for two reasons. One, when you're doing torques, it eliminates it. We'll call that F vertical, and we'll call this F horizontal. And also, keep in mind that the hinge actually does cause the system to rotate. So it's a natural place to put your pivot point, yes? To solve the torques about. Now, when you're doing this, you also always start with one force. You can always get one force, which is this sort of center of mass beam force, which would be mg. And you notice the rope goes down, so you'll have this tension in the rope, but you'll also have this tension in the cable pulling you to the left. So let's look at a clean picture of this, all right? Oh, it's again, incorrect. All right, so you can see here what the force diagram looks like, and you'll notice that if you sum the forces, let's set up the equation. If we sum the forces in the y direction first, actually I hate green. I'm just realizing I like green. I hate this green. Let's do red. So if we sum the forces in the y direction, that's the first thing we did, right? We get this F vertical, which is right here, right? In the y direction, we have minus little mg. And then we have minus tension in the rope. And that's all got to equal 0. But now we have two unknowns right here in y, so we're used to this. So now we notice we have an x component this time, so now we have to solve for fx equals f horizontal yeah, Mina.
Sorry, Professor. The tension, right, from the big box, the rope, um, when it's up at the end of the beam, we see
Yeah,
here it's been analyzed to the C and, is it C? I think C and Y component, I think. Yeah, C and Y components. So the tension, the number we get from the box, the other system, is it I is it the tension on Y, or is it the total tension? Like how
Well, the tension in the rope, right?
yeah.
I'd want to talk about the other system when we get there. I just want to focus on the beam.
Oh
But in
yeah.
order to get the tension of the rope, right? If you look at the safe, you just have mg down and tension of the rope up, right?
Correct. So the tension in that system is essentially equals the weight m times g. But when we transfer it to the system with a beam, how the tension translates there? That's what I'm.
Well, it's remember this is one object, this is the other object, right? And so
Mm-hmm.
Newton's law says those tensions have to be the same. There's no reason for them to change.
Okay, so it's a total for the tension on the box on one system is a total,
It's got to equal,
the
so this
sum.
TR has to equal this TR.
Okay, it's not that. It's a component of the. Oh,
Yeah.
okay, got it.
Yeah, no, it's not equal to TC by any means. You can't get that there. This is just the tension in the
No,
rope.
I was between whether it was Ty or the sum of Tc and Ty. That's where I was getting confused.
Right. Right. No, TC is only in the X direction and we're only in the Y direction, and yeah. And if you're looking at the rope, that rope only translates to those two.
Okay, got it. All right, thank you, Professor.
Okay? Yep, no problem. So in the X direction, we have FH, and then we have minus TC, and that's going to also equal to 0. So that equation was not helpful, right? Now for the torque, this is a somewhat easy system because it's uniform. We can call this length L and not really worry about its whatchamacallit, its actual distance in the X direction, because we can just say this is L over 2, and over here we're at L, right? So when we do our torque about our pivot point, we have 5 terms. 2 of them, it's going to equal FV times 0 plus FH times 0. One of these will be minus, so this will do clockwise, so FV is going to be minus, but it's 0, so it doesn't really matter, but I want to be correct with my right-hand rule. So we've eliminated, so this is exciting because we've eliminated 2 variables already without solving for anything. So now we have to go here, and if we look about this pivot point, this mg, we'll want to make this rotate. Actually, no, it's 0, so it doesn't matter. I'm just being silly. I picked another pivot point, but those 2 are 0, and they're 0 for good reason. So about this pivot point, mg will cause a clockwise rotation, so that's going to be minus mg L over 2. And we can look here and say, all right, we can, am I going to miss something? No, I don't think so. I just want to be sure. All right. And we look here and we can say that we have TC is going to cause a counterclockwise rotation, and TR will cause a clockwise rotation. Yeah, Mina. Yep. Question? Can't hear you. Okay. I'm just going to assume it was a mistake. So we can see that here, and now we have this equation. Again, the L's cancel out, and we will have mg over 2 equals TC plus TR. Now TR, as we already saw, we can probably get from, we have the big mg. So we can solve for TR from a secondary system, and this will give us, this will allow us to solve for TC directly. And once we have TC, we can solve for, and once we have TR and TC, we can get the vertical and horizontal components. Yeah, Mina, did you have a question? Because I couldn't hear you.
I did actually. I'm not sure what happened. I thought
Okay.
I was talking. I was asking, but something happened and my
Yeah, I didn't hear you.
So I was asking the distance. Is it L over 2 or L over 2 times cosine theta?
Well, you can really kind of, I mean, when you look at it, you can kind of do it either way if you really want to. I was just looking at the bar, and it's a distance. This is the distance from, it's the center. You don't have to do the cosine of theta here, because you're just, it's the torque is, oh, I see. Hold on. Wait a minute. Yeah. Because it's a perpendicular distance, not just the distance. I was being a little. You've caught it. I was just trying to make my life easier there. Yeah. So.
I'm afraid of math, so I was like, wait.
No. I messed it up, and I was looking over here. Yeah. No, you need to do a perpendicular distance. So what you could do here, the best way to do this, right, is to not say M2, is to have this, to put the sign phi there, right? Because if you look here, you can say that the torque is going to be equal to mg so this is your R vector, right? And you can show that this angle is theta. So you want to do mg sine of 90 plus theta, right? That'll get you there. Yeah. No, I even goofed up. I was getting ready for my next meeting and everything. Yeah.
Professor, sorry. The torque point, I thought we took the torque point as the hinge. No?
We did. And remember, so if the torque point here is at the hinge, this is the R vector. The R vector is along the beam.
So the distance, okay. For which vector are we looking to? Okay, now
Yeah.
I got confused. Hold on. Hold on. Okay, so if we have the hinge as a tipping point, right? And we're looking the torque, which is the sum of the weight of the beam.
Yeah.
With the distance between the hinge and the weight of the beam is essentially L over 2 times cosine theta.
Right. It's definitely, the distance here is definitely L over 2, right? Because we're halfway in between.
Plus,
so you want to do M over G. I'm just messing up here because I'm getting worried about getting to my meeting. So mg L over 2 sine 90 plus phi. You can see the angle.
Is it sine or cosine?
It has to be sine, because remember, it's got to be sine, because remember, this is the vector cross product. R cross F. That's what I'm doing. Equals R F sine of the angle between them.
Okay, I would have made a big mistake here, because I would have put cosine, because effectively I would count the distance from horizontally from O, the hinge, up until the lines that are blurred.
Right. That's the line.
But it's not that the distance. You're counting the distance vertically from the point of center of mass to the x-axis, essentially.
Right. So the hinge. So it's to sort of recapitulate. I want to see if what I'm saying is what you're saying. So you have your torque is equal to R cross F. Your R here, the length of that distance, is going to be L over 2. And that R vector is going to point along the beam. So now you have R here, right? That's your r vector, crossed with your f vector, mg, so that's the f part, and then sine of the angle between them. And the sine of that angle will be 90 plus theta. Okay?
I'm processing. I'm processing.
All right. Well, I think I really do have to run, everybody. I hate to leave on a
Okay.
question, Mina, but actually I think this is perfect because we're going to go over this one again tomorrow before we
Okay.
start on the homework example. So this is a perfect place to start because I think now you all see how complicated it can be too. So I think it's a perfect place to stop. I do feel bad running out on you in the middle of the question, though.
No problem, Professor.
So
Tomorrow.
I'll see you tomorrow, and we will start here and redo it, okay?
All right. Thank you,
And look at
Professor.
that homework, everybody. I already took a picture, and I will see you. Usually I'd wait for you all to go, but I'm running late, so I will talk to you all later.
All right. Bye.
I'm gonna